Today I'm going to be talking about detecting single gravitons with quantum sensing. First of all, I'll start talking about what I actually mean by the concept of particle detection in the context of gravitational waves. Then I'll talk about how we can enhance single graviton processes with macroscopic quantum systems to make this kind of particle detection more realistic. Then I'll talk about the concept that I've developed with collaborators including Srinath and my supervisor Igor Bukovsky and another PhD student at Stephen Institute of Technology on a gravitational version of the photoelectric effect with a quantum acoustic resonator. And then I'll conclude with some remarks on what this experiment would actually mean for quantum gravity. So when we think of particle detection in say, an electromagnetic context, we usually mean some kind of quantized matter system with discrete energy levels, which interacts with some external field and undergoes discrete transitions between those energy levels. And so, for example, in the context of electromagnetic radiation, this would be the detector absorbing a single photon and then undergoing a single transition to the first excited state. So these kind of photon detection processes were really key in the formulation of quantum theory in the early 1900s. For example, the Bohr model, where the atom undergoes transition between its bound states and absorbs and emits single photons, or the photoelectric effect, where instead of a transition to a bound state of the atom, you have a transition to a continuum of excited states, or the free electron with varying kinetic energies. Now, although the modern view of what a detection process is a process where the detector clicks when there's only a single photon input. So going back to the experiments from the 70s and the 80s, where the first experiments on measuring G2 functions were done, since then we've really thought of the concept of detection as being when this transition occurs when a single photon is present. However, the original studies of the photoelectric effect were not single photon input. They were stimulated processes where the wave the detector was interacting with was really of high amplitude, consisting of many, many photons, rather than just one photon. So the question that was set out to answer in this project was, can we observe a detection process, like I was just explaining, for the interaction between gravitational waves and quantum matter? And the conventional answer to this question is no. So Dyson famously did an analysis of whether it's possible to detect a single graviton, and there were two reasons for why he reached the answer no. He was using this more modern concept of detection, where when the detector goes click when there's only a single photon or a single graviton input. And they were only considering these processes for atoms, so looking at the graviton emission and absorption rates for really microscopic quantum systems. However, quantum mechanics is no longer limited to just atoms. We can prepare massive optomechanical systems in mass scales that are much, much larger, orders of magnitude larger than single atoms. So in our paper, we reached the contradictory answer of yes, and that is the basic concept is that if the gravitational wave can induce quantum jumps between energy levels of a massive quantum acoustic resonator, then that would be a gravitational analog of these photoelectric experiments from the early 1900s. And the key insight behind that is that you do not really need a single graviton input to infer the exchange of single energy quanta between matter and gravitational waves. And that's exactly the same principle on which the photoelectric effect works. So we don't need this modern concept of detection where the detector goes click when there's only a single photon or a single graviton input. If we want a detection in the sense of the early 1900s, which is what the photoelectric effect was, it doesn't matter if the gravitational wave is a coherent state consisting of 10 to the 36 gravitons. We can still infer the exchange of single gravitons between the gravitational wave and quantum matter. So the basic experimental setup we had was we proposed is a Weber bar, which is literally like a 2-ton bar that was originally proposed by Joseph Weber for detecting gravitational waves, but instead of just a regular gravitational wave detection, which would involve monitoring the average energy, what we propose is a continuous energy measurement, similar to the so Srinath did the analysis of the continuous energy measurement in this context. So it's nice that I'm following up his talk. But really, if you have a continuous measurement scheme like he was discussing in his talk, reading out the energy levels of this massive resonator, you can really resolve single discrete energy exchanges between the gravitational wave and quantum matter. So now we'll get into how these single graviton processes work for such a massive 2-ton gravitational wave detector. So linearized quantum gravity in low energy radium was first studied by Bronstein in 1935. And so when you go through and quantize the gravitational field perturbations, it results in gravitons in direct analogy to electromagnetism. So Weinberg's calculation was to take this quantized gravitational field and compute the rate at which an atom emits and absorbs gravitons. And when you do that, you get 10 to the minus 40 hertz. So nigh on impossible to detect a single graviton using a single atom. So the two enhancement mechanisms that I kind of touched on before are that we look at massive quantum systems. So quantum mechanics is no longer limited to just atoms. We can prepare massive systems on the order of kilograms even. So the LIGO mirror is a kilogram scale, and it's been prepared close to its quantum ground state. And we look at stimulated emission and absorption. We reject the notion that it's only a detection when there's a single photon input. If it's stimulated, we can still consider it to be a detection of some kind. And so, the main, as I was kind of discussing before, the main experimental protocol we look at is this Weber bar. So the way these Weber bars work is that it's, as I was saying, it's literally like a 2-ton. Think of like a massive cylindrical cylinder. And when the gravitational wave comes along transverse in a transverse direction to the longitudinal axis of the Weber bar, it excites oscillations along the longitudinal axis of the Weber bar. So think of these atoms as all being placed along the longitudinal direction of the Weber bar, and the gravitational wave really excites collective oscillations of those atoms. So it produces phonons in the Weber bar. And when you look at the interaction between the gravitational wave and this quantum matter system, the interaction scales with the number of atoms that are collectively oscillating and collectively interacting with the gravitational wave. So you get this enhancement. So you get this enhancement with the number of atoms that make up the Weber bar. So this will really help us bridge from that 10 to the minus 40 hertz from a single atom to something much, much larger. And we find that when you look at spontaneous emission, so that's this Weber bar interacting with the gravitational vacuum, the rate, if you initialized these phonon modes in the n equals 1 Fock state, and then looked at the rate at which gravitons are emitted from, say, the transition is from the n equals 1 Fock state to the ground state, and it would emit a graviton, the rate for that process to occur is 10 to the minus 33 hertz. So already much, much better than the atom, 7 orders of magnitude we've bridged, but we're still a ways away from getting this to something observable. So now we look at stimulated emission rather than interacting with the gravitational field vacuum. We just look at the Weber bar interacting with a coherent state of high amplitude. And for an aluminium bar close to what Weber had designed, and for the gravitational wave amplitude close to what LIGO had detected, you obtain 1 hertz. So the Weber bar and the gravitational wave exchange a single graviton each second. So that really brings this single graviton transition rate to something that we can actually realistically observe in a laboratory experiment. So this calculation I just showed you is Fermi's golden rule. So it's quite a quick and easy calculation to do, but it only applies for a particular situation, namely that when the Weber bar is interacting on resonance for a long duration. So if we want a more realistic model of the interaction, we need to account for the gravitational wave's frequency chirp. So the real detected gravitational waves that we know exist have a chirp in that their strain and frequency changes over time. So we need to account for that in our interaction Hamiltonian. And so what we did is we solved the dynamics to optimize we calculated the parameters that would optimize the absorption probability for a single graviton. Because in principle, the gravitational wave can excite higher energy levels in the mechanical resonator, the n equals 2, the n equals 3, the n equals 4 Fock state. But we really want to isolate this, the probability to measure the n equals 1 Fock state. Because if you measure that process, you can say you've measured that the resonator transitioned to the n equals 1 Fock state. That means you've measured a process where a single graviton was exchanged between the gravitational wave and the quantum matter system. So calculating the parameters that would be needed, we looked at a number of possible gravitational wave sources. The first 4 columns are for LIGO band gravitational waves. The next two are for expected continuous gravitational waves, and the last two are from speculative sources in the high frequency range. But our main focus was for these LIGO band gravitational waves, because if you did a detection in the LIGO band, or if you could get the quantum technology to work in the LIGO band, you will know with 100% certainty that you will get this experiment to work, as in you will be able to do a gravitational version of the photoelectric effect. There's no question of like, oh, will I run this experiment and even see anything, because I don't know if the sources exist. We know with 100% certainty that we will, if you can get the detector to work in this frequency range, you will see a signal. And so that was our main focus. And so zooming into the second column for this neutron star merger that was detected back in 2017, we looked at the parameters that would optimize the probability of absorption for a single graviton. And the required parameters for this absorption rate to be larger than thermal noise is what we looked at, are actually not that unfeasible. So, you only need to detect a mass of 250 kilograms, a Q factor of 10 to the 10. So the Q factor is if you ring up, if you have a single phonon in the bar detector, the Q factor tells you how many oscillations that phonon will undergo before the oscillation dies out. And the environmental temperature, 1 millikelvin, which is not that far off what can be achieved in current laboratory experiments in terms of the temperatures dilution refrigerators can reach. So let's compare this to what has been achieved. So in the last time these massive Weber bars were really in use, in real active use for gravitational wave detection, to the best of my knowledge, was in the 90s, before their funding got abandoned in favour of LIGO interferometers. And there they had a 1.5 ton niobium bar in Australia with a Q factor of 10 to the 8 and a frequency of 700 hertz. So if you look at that, that's compared to the parameters that we need, it's really not that different. And more recently, they achieved the same, or one of the same group achieved Q equals 10 to the 10 at megahertz frequencies. Okay, so that's much higher frequencies, but it's really showing you that these parameters are not really not impossible. However, there's one thing that I'm neglecting to mention, which is that in order to have a direct photoelectric analog, we really need quantum sensing. So we need projective measurements of the bar's energy levels. So this is what hasn't been achieved in a system of that size. So Srinath simulated the continuous measurement of one of these massive bar detectors, and so initially here you've got the bar detector initialized to its ground state, and then at about the 44-second mark here you've got the incidence of a chirping gravitational wave that closely mimics that neutron star merger that I was showing just before. And the simulation showed that for a bar of around 30 kilograms, you would for the particular measurement strength he was using in that simulation, you would see this collapse to the n equals 1 Fock state. And this would give a direct gravitophononic analog of the photoelectric effect, or the photoelectric case, where you have these discrete transitions between energy eigenstates of an atom. So what has been achieved in terms of this quantum sensing and being able to measure energy levels of these acoustic systems? And so most recently, to the best of my knowledge, the best that's been achieved is a direct energy measurement of individual levels of microgram mass acoustic resonators. So these are miniature, so they're phonon modes, internal phonon modes of these of the same work of the same principle, as in that they're acoustic oscillations of some bulk material. However, what they've been able to get these projective measurements to work for is only on the order of about microgram masses. So still many orders of magnitude to bridge on the quantum sensing side. So this experiment is not impossible, but it's still challenging. But what would it mean if we actually did it? So the three archetypal signatures of the photoelectric effect that we all remember are the threshold frequency, the independence of the ejected electron energy from the classical field intensity, and the near instantaneous ejection of photoelectrons. So in our gravitophononic setup, we have all these signatures. So we have a threshold frequency, namely that instead of photoelectrons, gravitophonons only get produced close to resonance, or when the gravitational wave frequency reaches a certain threshold frequency. And you have that when you produce these, when you collapse the system to the n=1 Fock state, you get that the produced gravitophonon energy is independent of the classical gravitational wave field amplitude. And in our case, the timescale for the gravitophonon production is the measurement strength. So that's the timescale for the collapse to occur, which is what the analog of the timescale for photoelectrons to be produced would be. So the caveat here is that, okay, the photoelectric effect was explained by Einstein in 1905 in terms of light quanta, but many, many years later, Lamb and Scully came up with an explanation for the photoelectric effect that did not involve the quantization of the electromagnetic field. And later, I believe later, James and Cummings came up with the semi-classical model of electromagnetic radiation interacting with an atom that we all study in undergraduate physics. And that model can account for transitions in atoms and the photoelectric effect without quantizing the electromagnetic field. So what does this mean for the quantization of gravity? So however, the caveat there is that these semi-classical models must violate energy conservation in that if you have a discrete transition on the matter side, if energy is conserved, that means that there must also be a discrete h bar omega transition on the field side as well. Of course, you can have a non-energy conserving theory where you still maintain a description of the gravitational wave as a classical continuous field that satisfies the Einstein equations, or in the electromagnetic case, a classical continuous field that satisfies the Maxwell equations. But in order to account for the photoelectric observations, that if you maintain that description, you have to give up energy conservation to explain the result of this experiment. So therefore, if you make the assumption that energy is conserved, the experiment is inconsistent with the gravitational field treated as a classical continuous wave that solves the linearized Einstein equations. So if you make the assumption of energy conservation, you have that the experiment provides some weak evidence for the existence of gravitons. So to summarize, the basic protocol is presented in the paper is that you have some compact binary in spiral. So two neutron stars merging or two black holes merging that emit gravitational waves. Then you have stimulated single graviton absorption in the bar detector at Earth. And at the same time, you're continuously monitoring the energy levels of the bar detector. And you see if a gravitational wave is present, you'll see a discrete click to the n=1 Fock state. And then if you correlate that detection event with an absorption, with a detection event at LIGO, then you can have a high confidence that click you saw in the detector was due to the absorption of one single graviton. So to conclude, single gravitons can be detected in the same sense as in the early 1900s with the Bohr model and the photoelectric effect. This can be achieved with not that unrealistic parameters. And it doesn't prove unambiguously that gravitational field is quantum, but serves as a test of the quantum nature of the field to the exact same extent as the photoelectric experiments of the early 1900s. And this is a subtle point because there are also arguments that to really prove the existence of photons, you need G2 measurements, negative Mendel-Q parameters. I mean, I would say that does, yes, it provides stronger evidence for the existence of photons, or in this case, the existence of gravitons. But it's more like that does not take away from the fact that the photoelectric effect still provides weak evidence for the existence of gravitons, or the photoelectric effect provides weak evidence from the existence of photons. And with that, I'll thank my collaborators, Srinath Manikandan, who is here in the audience, Thomas Beitel, who is a PhD student at Stevens Institute of Technology, and my supervisor on this project, Igor Bukovsky. And yeah, thank you.